Hey everyone, it's Mr. Canfield, BC Calculus, Chapter 11, Polar Coordinates, Area, and Arc Length. Okay, so basically two new formulas today, and just two more things to add to our list of stuff we memorized. So I've got my answer key open so I don't make any bogus mistakes as I go, and here we go. You're gonna need a calculator and your notebook. So if you go back to circles, if you've never found the area of a sector of a circle, easiest way to think about this is we are trying to find the area of a portion of a circle. Well, what's the total area of a circle? The total area of a circle is pi r squared. So basically what I need to do is I need to take my circle and just take a chunk out of it, and I want to find the area of that chunk. Well, that area, if we think about this as theta, if we're talking about this in degrees, it would be, this chunk would be theta over 360 of the whole circle. But we deal in radians in this course, so instead of being theta over 360, it'd be theta over 2 pi. Like however big that is, if it's 90 degrees, sorry, 90 would be 90 over 360, like it'd be 1/4 of the circle. But in radians, it'd be pi over 2 over 2 pi. But that's basically, we're gonna take this area, this, and we've done like a semicircle before where we just divide this by 2. But now we're just gonna say, well, we don't necessarily know what the angle is, but we're gonna multiply it by theta over 2 pi. Like whatever portion of the circle it is, hey look, the pi's cancel. So the area is equal to 1/2 theta r squared. And let me just make sure that that is what Stu got for his. Yes, it is. All right. So that's the concept. And what we're going to do is we're going to extend, just like we took area of a rectangle and we extended that into Riemann sums and extended that into integrals. We're going to take this area of a circle and extend it into areas of fun shapes like this, you know, or like this. And it's gonna be the same idea. Instead of having a constant length and width for our rectangle and we get a rectangle area, we have an infinite number of thin rectangles and they all different heights. What we're gonna be dealing with now is an infinite number of circles with different radius. And so the area of some generic polar function, let me just make sure I'm copying it down right. Yes, okay. So it's this radius that's changing. So we're gonna have the area of a sector be 1/2 from theta, whoa, not Q, theta 1 to theta 2 of our radius squared, d theta. And radius is going to be defined by basically the function. And so we can write the function as f of theta. So this is our formula as presented to us in our textbook, and he just leaves it as r, which is also fine. So like for this first example here, it says r is equal to 4 sine of 3 theta. So if we want to find the area of that, it literally is just going to be, we need to find out what theta 1 and theta 2 are, and it's going to be 1/2, it's going to have a d theta on the end, and in here, it's going to be our radius squared, 4 sine 3 theta. So to do that, it can be helpful to look at this. I tried to draw what this looks like a minute ago. Wait a minute. I'm not going to be able to graph this in here. These are y equals. I need r equals. So you push the mode button and you go down, and you know we've done parametric graphing. Now we're going to do polar graphing. Just a heads up, the last one is called sequential. What it'll do is it's normal function graphing. It'll just graph one after the other. I think, oh no. I don't remember. There's something weird, but it's just like regular function graphing. Oh, wait. Oh, it deals with sequences. All right, hey, I'm not restarting the video. I forgot. All right, so 4 sine 3 theta. So notice when I push X, theta shows up instead, and we'll throw this. Ooh, careful, careful, careful. Don't, I was about to start typing the rest of it. We want to graph this and see what it looks like. So I'm going to zoom, and I'm going to zoom trig. So that is what this looks like. And so what's going to be beneficial for us is to, since we deal with sine and cosine stuff, it generates symmetric things instead of having to deal with all the different zeros and stuff. It's so much better for us to just start at wherever one of these petals starts and end where it ends. So what I can do is trace and see, it looks like, all right, it looks like theta, we're getting to like 1 for theta, which might not be readily apparent about what value of theta that is. So let's think about this. When is this tangent to the pole? So sine is equal to 0. All right, hold on. Let me just 4 sine 3 theta. Here's what I like really would do. And I probably would mentally go through and do this. I want to make sure I'm clear here. So let's see. So sine of 3 theta, I divide both sides by the 4. 0 divided by 4 goes away. So sine of 3 theta is equal to 0. So that means that sine is equal to 0 at, what, pi? Oh, 0 is another one. 2 pi, etc. So that's not theta though, that is 3 theta. So to find out what theta is, I'll divide those all by 3. So I think I should be able to just to go from 0 to Stu says negative pi over 3 to pi over 3, but I think it's just 0 to pi over 3 is going to get us there. So let's, what I'm going to do just to double check is I'm going to go in here and I'm going to change my theta min from 0 and my theta max to pi over 3. So all that's going to do is it's going to draw this, but just from 0 to pi over 3. Yeah, okay, so that gives us our first petal there. So all I have to do is now use my calculator and get this integral. So, oh wait, so I'm going to go from 0 to pi over 3. Right, so, oh, forgot the 1/2 out front. So 1/2, 0 to pi over 3 of 4 sine 3 theta. I'm going to write 3x. Oh, I'm in polar mode, so it does it for me. Okay. Oh, I forgot the parentheses before the 4 sine and after. And then I'll throw my squared in there. D theta. And we get this number. So that is the area of one of our petals. So if I multiply this by, sorry, I'm just looking at Stu's answer. Did he get a different answer than us? So I'm going to divide this by pi and see what the fraction is. Okay, so this is 1/3 pi. We get 1/3 pi as our solution here, and then we'll multiply it by 3. And so our answer will be, oh, so I could have just taken this and said times 3, and we would see, oh, look at that, it's exactly pi. So, all right, so that'd be the area of this. There's a couple typos in his work, so I think this might be like an old version that I'm looking at. All right, so yeah, the area of that would be pi, exactly pi. So sorry for the long pause there, but hey, that's what speeding up the internet is for. All right. So our next one, oh, that's one reason why I have trouble with this section is not everything lines up with, oh, every year I struggle with this section. That's why I have the answers open right now. I need to get a new answer key. So it says find the area of the region lying between the inner and outer loops of the limaçon. I don't know, Limacon. I think it's limaçon because that little curly thingy under the C. So let's look at what this looks like. So 2 sine theta, close it off, -1. There's our graph. Okay. So look at where this one starts. We go from 0 to just pi over 3 here. It starts here. So finding our tangents to the pole is going to be important. So, all right, let me just go back and say 0 to 2 pi. Let's see if 2 pi is enough to do everything. Okay, yeah, so looks like that's our 0 and 2 pi. And so what we're going to be doing is we are going to have to find a couple different areas. We can find the area of like the whole thing, and then we've got to find the area of the inner loop, and we're going to have to subtract them. So first let's find our tangents to the pole. So we know that 2 sine theta is equal to 1. So if we set that equal to 0 and we get 2 sine theta minus 1 is equal to 0, we'll add the 1, we'll divide by 2, and so sine of theta needs to be 1/2. And so we get sine of theta is 1/2 at pi over 6 and 5 pi over 6, which to find, we use our triangle. Well, if sine is 1/2, then that's going to be a triangle that has SOHCAHTOA, OH, so 1, 2, and then this will be square root of 3. So this is a 30-degree angle. And then I want to find anywhere else I can draw a 30-degree angle that it would give me a +1 like that, and it's over here. So this 30-degree angle as well. Remember 30 is pi over 6, so the pi over 6 that's above 0 is just pi over 6, and the pi over 6 that's right before pi is 5 pi over 6. So that's the super quick version how we'd find that. So if we look here, let's go to, let me zoom. No, it didn't do it. So I draw the whole thing. I want to zoom in a little bit. Okay, cool. So I want to find, when does it start drawing the inner guy and when does it end drawing the inner guy? So I'm going to trace, and it looks like 0.5. So is that pi over 6? Yeah, it looks like, so at pi over 6, it looks like it starts doing it, and then goes, and then 2.61, is that 5 pi over 6? Yes, okay, so the inner circle is going to be from pi over 6 to 5 pi over 6. So we can say 1/2, 2 sine theta minus 1 squared d theta. That's going to be the area that we need to remove. And then the other area is going to be, so it's a little bit tricky. It's going to be before that, before the pi over 6, and after the 5 pi over 6. So what we could do is we could just say, well, you know what, let's go from 5 pi over 6 all the way up until it hits that dot again. So, we're going around the circle, 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 around the circle. We come back, oh, so my calculator stopped here, but we come back, this is 2 pi. How much past 2 pi does it hit again? Pi over 6 past 2 pi. So what I can do is I can say, we'll go from 5 pi over 6 all the way up until 2 pi plus another pi over 6. So 2 pi is 12 over 6 plus another over 6. So that's 13 pi over 6. And this will give us, that'll give us, ignoring the like the donut hole, that'll give us the rest of everything, like the whole thing shaded in. So what we'll do is we'll find the whole thing and we'll subtract out that little donut hole, and it'll leave us with that area. So I can do that in one step if I'm careful. I mean, oh, why did I erase that? Oh, I should have done this last time. 2 sine theta minus 1. Especially if I say, let's see, so I'll go from pi over 6 to 5 pi over 6 of r squared, which I can use if I do the alpha f4, I can do that. The other way to handle this, and you might be like, Mr. Canfield, you didn't do the half. I know, I'm gonna do the half at the end. I'm just gonna divide it by 2 at the end. Another way that we could have done this is we could have said 5 pi over 6 to 13 pi over 6. If you can't do that alpha trick like I did, the vars button, this brings up a lot of different variables that we can mess with. And if you go over to y vars, we're in polar, R1. So that's another way to do that. So I'm going to take this minus this, divided by 2. I got 8.337 or 8.338. It's not equal, it is approximate. All right, so that's how this works. So let's move on to our next one. I think that, okay, there's a few more to this. So our next one says, take this like weird looking thing and subtract out the circle and give the dude an afro. So all we gotta do is find the area of the whole thingy and then subtract out the area of the circle. So hopefully the area of the whole thingy or hopefully the whole thingy just yeah, it's just okay, it just takes 2 pi to do, right? So 0 to 2 pi, that's not hard at all. So let's do 0 to 2 pi of r squared d theta with the 1/2 out front. And then we're just gonna subtract whatever the area of this circle is. Oh gee, and the radius is 2, right? So, oh wait. Oh, no, I'm underthinking this problem. If this circle was completely in there, that's what we could do. But we've got a much more complicated situation here. Look, there's parts where it's not overlapping. So we're gonna have to find out, hey, where is it overlapping? And just for those parts, so we'll find like our whole afro, and then we're gonna have to subtract out bits of this. Much, much more complicated. So first we gotta find the intersection. Fortunately, we do have that r is equal to 2, so we can find the intersection by setting 2 equal to 3 plus, oh, I'm off screen, 3 plus 2 sine theta. So we'll subtract the 3, divide by the 2, get negative 1/2 is equal to sine theta. Works similar to the last problem. Well, if I need it negative, then it's like this. So it's negative 30 degrees on both sides. So we'd say negative pi over 6 and 7 pi over 6 are gonna be the two places that they intersect. So then what we're gonna do is, so that's here and here. That's negative pi over 6. That's 7 pi over 6. We're gonna basically have to subtract these guys. And this is gonna be, just take the one area minus the other area. And you could, so we don't actually want the entire circle area this time because of that bottom. So you could say go from negative pi over 6 to 7 pi over 6. of, we can call this R1, we can call this R2 if you want, right? Of R1 squared d theta minus 1/2 from negative pi over 6 to 7 pi over 6 R2 squared d theta. Now R2 is just 2, but like we could do that. Or since they have the 1/2 and the bounds are the same, we could just say 1/2, go from negative pi over 6 to 7 pi over 6, and do R1 squared minus R2 squared d theta. Just like when we are taking different areas and we minus them, we do top minus bottom. We're doing outer minus inner. That's all it is. So we go through, we do that, and I've already got the thing set up. So 9, we'll go from negative pi over 6 to 7 pi over 6 of R1 squared minus R2 squared, which is just 2, which is 4 d theta. I forgot the 1/2, so I'm gonna do times 0.5 at the end. And I got 24.187, which is the same thing that Stu got. So, all right, and our next one takes the same two functions, but this time is saying instead of finding this outer area, now we want to find this inner area, which if you are careful, intersection points are the same, right? So 7 pi over 6 and negative pi over 6. Sneeze. Thank you. All right, so what we're going to do for this, well, from negative pi over 6 to 7 pi over 6, it's just the area of the sector. So that's 1/2 4 from negative pi over 6 to 7 pi over 6. And that'll give us all that. We just need to find this little like mustache area here. It's a person, okay? And so to do that, we would go from, looks like 7 pi over 6 to negative pi over 6. Oh, wait, no. To what, 13 pi over 6? No, 11 pi over 6, 11 pi over 6. Yeah. 7 pi over 6 to 11 pi over 6, and we would just do the area of this part here, which is the function. So it's R1 squared d theta. So it's gonna be like these two chunks. Oh, Stu, you silly. He does it a little bit differently than me. But so instead of going from 7 pi over 6 to 11 pi over 6, he's like, well, it's symmetric. So he just goes from 7 pi over 6 up to 3 pi over 2. He stops at the halfway point. But I want to finish drawing the mustache area. So, so if we set all that up, 0.5. Negative pi over 6 to 7 pi over 6. 4 d theta. So the first part is 8.3775804, whatever. It's all that mess. The second part, no, goes from 7 pi over 6 to 13 pi over of. Do I still have it in there? I do, okay. Of just our function, squared d theta, so plus 6.8864. So we add those up. Got a slightly different answer than Stu here. Let me see if I'm missing something. Sorry, just I don't have a way to pause these things that I know of. Oh, is there a pause button? No? iPhones are funny. All right, so. Could have made a typo. Oh, I did. This was supposed to go from 7 to 11. Yeah, okay. Now we got the same answer. So, unfortunately, when we don't have access to the answer key, we don't always know when we made a typo. I made a baby mistake there that messed up my answer, but the written part is correct. So that's really where it's important for us to know that when we do these, the showing your work, showing what you're about to type in is super crucial, because when you make a dumb typo and you don't notice it, you have no idea. Like, it was gonna be what, like 15 versus 10.376. Like, it's essentially all meaningless. It's just these random looking numbers. I don't know what's right and what's wrong just from looking at the numbers sometimes. So let's see, because a polar point may be represented, let's see, in more than one way using polar coordinates, you have to be careful in finding intersection of two polar graphs. Your calculator does not have an intersection function in the polar model, so we do it algebraically. So kind of like we were doing earlier. And you do have to be clever and careful. So I'm gonna skip these. I can't remember if arc length of polar it shows up, so I'm gonna pause on that right now and go double check, because he goes into arc length and surface of polar stuff, which arc length is just another formula. And you might notice that the arc length formula is arc length polar formula is very similar to our other ones. So it's not hard to just add that on, but if we don't need it, I'm not gonna cover it. So that should help for the first chunk of the area. So we're just gonna do 1 to 6 on this homework assignment, at least for now. So hope that was helpful. Bye.